So this first lecture will basically be an overview. So I don't plan to be very detailed, and the following two lectures will be somewhat more in depth. So one theme well, of these lectures and in general is that the geometry gives a great insight into abstract algebraic and, well, algebraic topological structures. So we saw that, for example, in a talk of Muhammad, where some geometric considerations led to some leads one naturally to consider some curved notions of spectra and stuff like that. I think we saw that also in the talks of Mike, and probably we'll see more of that in the talks of Janko. So one classical thing in this direction is kind of Pontryagin classes. So these are defined as follows. So if I have a smooth manifold, then I can complexify the tangent bundle. So complexify. And then I can look at these classes pk defined by as Chern classes of the complexified tangent bundle. So these are these are in H4K MZ. So these are integral classes. One can also consider the rational classes. So let's say PQ KM. So the image inside H4K MQ. So these especially are very interesting because they're highly amenable to calculation. In particular, we have this theorem of NOVIKOV, rational Pontryagin classes are topologically invariant. So maybe I should kind of split. Invariant. So note that they are not homotopy invariant. So, not homotopy invariant. So this is a very, very deep theorem, and it has some profound applications as well. What I would like to talk today is a kind of so would like to discuss a kind of a quantization. A quantization of And exactly what quantization means, well, I'll give you a better idea in the second lecture. So right now, it is kind of just. The rational Pontryagin classes are not homotopy invariant. Here. I don't know. I think not, but perhaps a Google search. In any case, well, I do not know. Yeah, I do not know. So, okay. So what's the idea? Well, just thinking in terms of tangent bundle again. So after complexifying, we can projectivize. So so you're just taking a bundle and you're fiber-wise projectivizing. So you're going to get, so if this is dimension R, then you're going to get a CPR -1 bundle over M, maybe, right, BTM here. And so now you can do something interesting. So remember, in the talk of Sushmita, one can define a certain Fukaya category associated to every symplectic manifold. So here we have a fibration. So actually, this has a bit more structure. This is a fibration with structure group PUR. So structure group fibration. And so we can sort of look at the associated family of Fukaya categories of the fibers. Sorry, let's just try it. So family P goes to Fuk P TM P. So actually, yeah, well, okay. I think later I will change this by X. In fact, maybe I should change it now. Yeah, let's change it now. So let's do. Okay. So just to remind you, because well, Sushmita didn't really get to the actual Fukaya category. She defined the A-infinity algebra. So basically, you have a category. So this Fukaya category of a symplectic manifold. You have objects, Lagrangian submanifolds, and so morphisms are intersection points. So, well, let's say Q vector space generated by the intersection points. So, home. Right, and then, so this is actually chain complex. So let me just say here, it's a chain complex. Chain complex over Q. Chain complex And the differential is given by counting holomorphic strips. Right. Okay. Oh, sorry. Thank you. So, well, so in the case of CPR -1, we can do something a little bit simpler. So for concreteness, take objects of Fuk CPR -1 to be Lagrangians, Hamiltonian isotopic, to RPM -1. So this kind of cuts down the space of objects considerably. Okay, so now this is somewhat more explicit. You have kind of a family. So the problem is, what do you mean by family? So just like you have a vector bundle, if you just look at the associated family of vector spaces, and if you forget the topology, you lose all the information, right? So just thinking of the family of vector spaces parameterized by the points of the base, there's no information there. So in the same way, you really must use more geometric information of this bundle in order to give this word family some meaning. Just everything Hamiltonian isotopic to RPN -1. Sorry, RP R -1. Well, yeah, I mean, just a linear RPM -1. Sorry? S. Well, they're all isomorphic, but. Well, yeah, but just like I mean, you have a notion of groupoid, right, where all the objects are isomorphic. You still want to think of them as being distinct, right? So a groupoid is the generalization of a group. So in the same way, you want to. I mean, otherwise you're gonna run into trouble because of you cannot just take one object because you're going to run into trouble by thinking of this in terms as a family. Yeah. So. Right, so as I was saying that, so here, need to use more geometry to make sense of this. So in a sense, that's a very tricky problem, actually. So. Okay. So the first step to getting this resolved is I'm going to describe a construction. So now in more generality, given a Hamiltonian fibration, so this just means a fiber bundle with structure group Ham M omega. So this is the group that was discussed today already. And so associated to this, I'm going to describe the construction of a functor which goes from the category of smooth simplices of X into the category of infinity categories. So the simp X so it has objects smooth maps and yes, X, and morphisms commutative diagrams. So let me give this, well, right, yeah. Anyway, so commutative diagrams like this, where the top arrow is simplicial. So this is simplicial. Okay, and A infinity cat is just, well, it's just a category of A infinity categories. Okay. So is that clear so far? Well, so in fact, I can tell you right away what to do with points. So you just set this to be Fukaya category of the fiber. Now, for general simplices, you have to you need a bit of topology. So so in general, we need the following. So okay, yeah. So okay, so let RD be so the moduli space of D-1 marked disks or D-1 punctured on the boundary disks. I think actually it was called RD-1 in Sushmita-Stock, but well, I'm shifting this subscript to be better, well, to better coincide with the Stashev space KD. Okay, and then we have yeah, actually, well, I guess well, let's make the convention that I'm always talking about compactified. So the compactified and so then you have the universal curve. Right, so so this is, so more explicitly, this is the universal family of D-punctured Riemann disks, right? Okay. Okay, so why am I going with this? So what I want to do is I want to construct some natural maps. So there exists a system of natural maps. Well, call it UD M1 MD so this is over actually maybe N. This is over D. To from the universal curve to delta n. What I want to say is this. So it's a system over D, M1, MD, and N. Well, not quite. So let me write circle here. So this circle means that I remove the nodal points of the nodal disks. So if my disk is like this, then I'm going to take out this node, remove the node. It'll be disconnected. It'll be disconnected, but in the structure of the space, you want to remember how to glue it back together. So that's part of the structure. And so the other thing that's actually part of the structure is that we have here, so together with choices of strip-like ends. So right, so we have, so pictorially we can think of our punctured disk as something like this, and so this is kind of in the hyperbolic, from the hyperbolic point of view, and you have identifications of the ends with, well, you have strip-like charts. You have charts phi time. Yeah. So phi 0, 1 times r plus to, well, to the surface, to the end. So deparameterize the ends, the open ends. I don't really know. Okay, that's part of the structure, and well, and actually you have the same thing at the nodes. You need to keep the structure. But that's not so important right now. So yeah, and so these maps satisfy. So these maps satisfy certain axioms. And so I'll tell you about this. I'll tell you about this in more detail in my last lecture. And they're unique. These maps are unique. These are unique up to homotopy. Through maps satisfying the axioms. So this is a certain connection between the universal curve of Riemann surfaces and the standard topological simplex, which as far as I know, hasn't been known before. And this could be of some independent interest. I'm not sure. So, okay. But let me, so like I said, I won't discuss these axioms in detail. It'll take a long time, but let me just give you an idea. So for example, if we look at S2, this is just, well, you can just think of it like this. And you have a map. So let's say, let me label this 0, 1, 1, 2, 0, 2. Two, 2. Right, actually, I forgot to say that. So these M1, MD, so the M1, MD are just labeling edges of delta n. Edges kind of composable edges. So the end of the edge is the beginning of the consecutive edge. So, well, you'll see in this example. So what is going on here? So, so these labels tell me that I should map this end to the 0, 1 edge, this end to the 1, 2 edge, and this to the 0, 2 edge. So I want to map this to the standard topological 2 simplex. So standard 2 simplex. Okay, so what can I do? Well, basically, well, I guess it's kind of clear. So I'm going to collapse the edges of my surface to the vertices. So this will get collapsed to so 0, 1, 1, 2. So right, this gets collapsed to 0. This gets collapsed to 1. This gets collapsed to 2. So you collapse the edges. These sides to the vertices, and the ends. So at the end I have. So at the end I have strip coordinate chart. Right. So I have a strip coordinate chart like this, and in this strip coordinate chart, I just send the slices, so the slices 0, 1 times S, say, to the corresponding edge of the 2 simplex. So perhaps it would be easier if I draw my 2 simplex on top of this. So kind of like this. And right. So you collapse like this, and the edges get collapsed to the vertices. Kind of like that. Yeah, that's not the best picture, let's say. So the universal curve. So this is a curve. So this is just algebraic geometry name. It's just a universal family. It's just a universal family. So the fiber over a point is the corresponding Riemann surface with. Sorry? Yes. Yeah. So you have a map. Right. Yeah. Right. So, well, they're parameterized by D. Its choices M1 to MD and N. It is for the whole space. It's mapping. It's a total space. It's the total space of the universal curve, SD. Yeah, yeah. So I'm still struggling to draw this picture, but perhaps I shouldn't have attempted. But let me. Okay. So is it clear now what this map is supposed to do, right? So yeah, so this is the surface. I'm just rotating it slightly, and so this is the end 0, 1. You just collapse onto the edge. Here I have 1, 2. Here I have 0, 2. And then the edges get collapsed to the vertices. Okay, so let's try now for S3. Just one more to give you. So S3 or S3 circ. Well, so I can so the corresponding space R3 is just the interval, and so here I'm going to have so I want to break here, and then I want to say. Right. So maybe something like this, and then on the other end you have and it might be better if I draw this as circles, but anyway, I'm not giving up now. So compose Right? What do I want to say? You. Okay. So these breaks, I mean, I'm drawing these breaks here. So this is because I'm disconnecting my universal curve. So that's why I have this break here. Okay, so let's label this. So let's say 0, 1, 1, 2, 2, 3. And 1, 2. 0, 3. And 2, 3. Yeah. Right. And so I want to tell you how to map this to the 3 simplex. So as before, so the end labeled by 0, 1 is going to go to the edge 0, 1, and so on. Likewise. And so let's see what to do with this curve here. We're going to so I have 0, 1, 1, 2. So I'm going to send this component to this face. Right, so that, right, kind of in the same way as I do there. And this I'm going to send to, so I have 0, 2, 2, 3. It goes to the bottom face. Well, so bottom face. And well, so that's for the fiber over 0, right? So, and then the fiber over 1, you kind of reverse happens. So you're going to cover this face and the opposite face. So, and then there is an interpolation. So for some general parameter, you have to interpolate for general fiber. Interpolate. And you want to do this so that this map, just call it U for simplicity, is degree 1. Okay. I mean, you can kind of see how this works. You kind of just sort of push. Well, yeah, I can't even visualize myself, but you push to the other configuration. Right. So actually, these maps are constructed. These are the existence is proved theoretically. There is no constructive procedure. So. Sorry? Sorry, can you repeat? Yeah, so in this picture, so you have, remember I have a chart here as well. I have a strip chart here. So in this strip chart, this end is going to be mapped to the 0, 2 edge. And likewise, I have a chart here as well, and in that chart, you also get mapped to the 0, 2 edge there for the blue component. So that's okay. So, any questions about this picture? I think first you really have to understand this. So, so these are ends corresponding to the punctures. Right. I think I meant d plus 1. Yeah, d plus 1. Sorry, thank you. Right? So then it's the same as, yeah, right. So it's like in your talk about plus 1, right? Or d plus 1 puncture, right? Yes, thank you very much. So here S2 has d plus 1 punctures. Okay, so anyway, so this is some preliminary topology theorem that you need. And like I said, so the existence is not constructive, but you just kind of inductively, there's some inductive procedure to do this. I mean, you can also construct it, but it's very, it's very complicated. So anyway, so I wanted to tell you, kind of as a very first step, is how to define FP sigma. So FP sigma, so this is an infinity category. Infinity category for sigma a two simplex. Okay. So, right. So to this end, so the morphisms, the objects of F sigma are, so these are Lagrangian submanifolds of pi for so pi is just p xi, where xi is the composition. It's the image of point goes to ith vertex, and then I mean, it's just the image of the ith vertex. So there are I goes from 0, I is 0, 1, 2. So maybe it's better to just say it's just image of the ith vertex, right? Image ith vertex. So hom Li Lj. So for Li in so, well, for Li in Fuk Pxi, Lj in Fuk. Okay, so let me just draw a picture. So I have my my two simplexes. This is the image of the two simplex inside X. I have the fibers, and in the fibers I have let's say Li, Lj. So this is the ith vertex. This is the jth vertex. And what are going to be the morphisms? So to define the morphisms, I'm going to fix a Hamiltonian connection on my fibration, and then I'm going to look at the flat sections of the Hamiltonian connections. So let me elaborate on this. So fix a Hamiltonian connection on our bundle. So, so what this means is, well, so we have a structure group Ham fibration. So abstractly, I can talk about an Erzman connection for this fibration. Or more concretely, you can do it like this. So this is given a trivialization, kind of, so yeah, that's right. So given a trivialization, phi alpha star alpha is a certain connection on 0, 1 times m. So it specifies horizontal spaces. So I can just completely characterize it by telling you how it lifts DDT. So DDT is going to be some vector field. And the point is that this vector field is Hamiltonian. This is a Hamiltonian vector field. Yeah. So this vector field is the horizontal vector field lifting DDT with respect to phi alpha star alpha. Okay. So when I say I want my morphisms to be flat sections, so I want flat sections with ends on the corresponding Lagrangians Li, Lj. Right? So, of course, from this, trivializing like this, you can see that this is exactly the same as what Sushmita was talking about when she was talking about defining the A-infinity algebra by, in terms of Hamiltonian chords between the corresponding Lagrangians, right? So flat section like this, if you trivialize, it just gives a Hamiltonian chord in this trivialization for this vector field for this time-dependent family of Hamiltonian vector fields. Okay, so let me just write this in words. So hom Li Lj is Z2 graded vector field chain complex. Z-graded chain complex over Q generated by flat sections of right. So flat sections of sigma upper star P over the ij edge. Right. So I pulled back my fibration. I look at the ij edge, and I'm looking at flat sections over the ij edge. So for sigma upper star A. I deleted my A here. Fix some Hamiltonian connection. Sorry? No, they're in different fibers. Yeah, they're in different fibers, so they don't intersect. So you're looking at, but of course, I mean, to get a correspondence with the picture of intersecting Lagrangians, well, so you take this trivialization, and then if you parallel transport Li to the fiber here, you're going to get two intersecting Lagrangians whenever there is a flat section, right? So you disagree? Sorry? Oh, okay. Okay. Okay, so I told you how to define the morphisms, and so let me tell you how to define the mu2. So mu2, say gamma 0, 1. So these denote the morphisms, say from 0 to 1 and 2. Lagrangians labeled 0 and so L0, L1, L1, L2. So okay, so let me first tell you pictorially. So let me just let me redraw the picture. Have here L0, L1, L2, and I have a morphism here, and a morphism here, and I have to get a morphism. Here. So this is, and let's say this is just gamma. So this is going to be the count of elements in the moduli space gamma 0, 1. And let me write 0 here, like Sushmita, meaning zero-dimensional. Gamma 1, 2, gamma. And this consists of A-holomorphic sections. I'll say what this is in a second. Of sigma alpha star p, asymptotic holomorphic, right? Sections of unit to asymptotic to gamma 0, 1, gamma 1, 2, gamma, gamma. Okay, so I have a fibration over this triangle. I have a Hamiltonian connection, just a pullback Hamiltonian connection. Then, and I have these flat sections, right? So, and remember, I also have. So this is where these maps U come in. So I have a map here from. I have a map to the base from S2, right? Okay, so let's say this is U. So, right, so to expand, really what I mean is not holomorphic sections of this, but rather of, and so, well, this is kind of informally what I want to say, but so more formally, so U of a star A holomorphic sections U of a star sigma of a star. Sorry. Well, let me just say A holomorphic sections of U of a star sigma of a star B. So pull back the fibration here. So the advantage, of course, being is now that now our base is a Riemann surface, and I can actually talk about I have a Riemann surface. I have a fibration over this Riemann surface, so I can talk about holomorphic sections. And asymptotic just means that as you go to the ends, you are asymptotic to the flat section corresponding to gamma 0, 1, like here. So I have some visualization here. And as I go out, here I want to be asymptotic to gamma 0, 1. And likewise, at this end, I want to be asymptotic to gamma 1, 2, and here to gamma. Okay, so the only thing I didn't say is what the hell A-holomorphic means. So A-holomorphic means J-holomorphic for the almost complex structure induced by A as follows. So J preserves horizontal subspaces of A. The projection, so the projection from sorry? No. No, they're all still in different fibers. So this fibration is still non-trivial. So it's a non-trivial fibration. Well, I mean, it can be trivialized, but it hasn't been trivialized because there's no natural trivialization. So this is still a non-trivial fibration, but the point is that the connection A is flat over the ends. So it's flat and R translation invariant. Basically by construction, because the ends gets, well, it's by construction R translation invariant because the ends get collapsed to the edges. So when you pull back the connection, you will get naturally R translation invariant connection, right? But anyway, I mean, you still have a non-trivial fibration, so that over the slices, it's identified with the fibration over the edge. Sorry, I mean, I'm talking about this one. So over this slice, the fibration is identified with the fibration over the edge. And so it makes sense to say that I'm looking at sections which are asymptotic to gamma 0, 1, gamma 1, 2, gamma. Right? So. Right, I mean, and well, so analytically, the point is that, so, I mean, it's crucial that you have a flat connection, flat R translation invariant connection, because so that guarantees that if you have something with this property that you asymptotic to flat sections, then the L2 energy of your section will be finite. So. Sorry? No, it's just, so this is just a smooth fibration. Yeah. J is defined, so, okay, so here I have U alpha star sigma alpha star P. This is a fibration. Yeah, so maybe I should write it here. So I have like U alpha star sigma alpha star P. So it's fibering over this Riemann surface, right? It's a Hamiltonian fibration over a Riemann surface. So there I can talk about a complex structure, right? And so this complex structure is what I'm now describing. Fiber-wise, it's fiber-wise tamed, which is enough because all the bubbling is in the fibers. So, right, yeah. I mean, I haven't yet finished writing it, but, right, so, okay, so, so A-holomorphic. Yeah, so let me expand this a little bit. So it's J-holomorphic with almost complex structure, J on U alpha star sigma alpha star P. Induced by A as follows. So J preserves the horizontal subspaces of A, and the projection, so the projection is J-holomorphic, and it finally J preserves the vertical tangent spaces. So, so these conditions don't characterize it completely because, in principle, I could vary my J in the vertical tangent bundle. So, I mean, these conditions uniquely determine J on the horizontal spaces, but on the vertical tangent spaces, I have some freedom. But anyway, so you pick any J which has this property, and I mean, well, strictly speaking, the choice of J on the vertical tangent bundle should be specified in advance and fixed once and for all. But anyway, so this is what A-holomorphic means. So, of course, so the point of the other maps UD is that we can define A-infinity relations. So, okay. So, the maps UD that I was talking about before, I used to define the infinite relations. So that you get an actual infinity category. And in the same way, you do this for higher dimensional simplices. How much time do I have? Okay. Okay, so we have an arguably very, very complicated object. We have a functor so an obvious question is, can we get something simpler out of this? So the first guess would be take the colimit. So colimit over simpex of FP. So this colimit probably exists. So this probably exists as an infinity category. But it is impossible to prove that it's invariant of all the various choices that you have to make. So, so far I just talked about basically my perturbation data consisted of a choice of a Hamiltonian connection A. But this kind of vastly simplifies the story. There are other choices that you have to make to actually define all the analytic moduli spaces. And so as you change this data, you would have to check that this colimit is independent up to quasi-isomorphism or something of the choice of the data. So this appears to be impossible. So and basically the reason for that to check independence of perturbation data. And basically the reason for that is that when you change the perturbation data, you're not going to get a natural transformation between the corresponding functors. It's kind of not how, that's not how Floor theory works. What you're going to get roughly is some kind of concordance, which is something more complicated. And the colimit does not behave well with respect to concordance. So you have to do something else. And this also brings us to the beginning picture of thinking in terms of a family of infinity categories. So what we do is we use this functor to construct a map so this is the singular simplicial set. And this is a certain simplicial set which we can think of as the space of infinity categories. So okay, so hopefully I'll have time to say a little bit about that today. So first, I suppose I have to remind you what are simplicial sets. So simplicial set well, on a basic level, it's a set so a simplicial set X under dot is a set X under dot n for each n greater or equal to 0, and maps fj from x dot n to x dot n minus 1 for j between n and 0. Is that right? The face maps. There are n faces. There are n plus 1 faces, right? So these are called face maps. And then you have maps dj and this is again. So these are called degeneracies. And again, there are n plus 1 degeneracies, right? So just so that you have a more concrete picture, we have the singular set of a topological space X is defined by is smooth maps, continuous maps. Okay, and well, and the face maps and degeneracies maps, I suppose, are clear in this case. And then these, of course, have to satisfy certain identities, and you can basically figure out identities from this example. I actually don't remember them off the top of my head, but you just you can figure out from here. Okay, so right, so and this is some space that I have to tell you in 10 minutes what it is. So it's a simplicial set. So S0 is just the set. Let me put here quotes of infinity categories. Then S1. So an element of S1 is an infinity category C, which, let me just draw it as a one simplex, and have, together with maps, C0, C1, from C0, C1. So together with full, faithful embeddings which together are surjective on objects. So surjective on objects. And are quasi-equivalences. And I0 are quasi-equivalences. So I suppose we haven't really talked about quasi-equivalences. So a quasi-equivalence between two infinity categories. Well, it's a morphism of infinity categories, so that when you pass to homology, so you take homology of all the spaces, it becomes an equivalence of categories with the associated vector-enriched categories. Okay. Okay, so a one simplex with these two faces, with faces C0, C1, which are the boundary points, is this structure. And so for a two simplex, so let me just do this really fast. So simplex. So again, I'm just gonna write it. I mean, this is just an infinity category, and then you have morphisms from one simplex corresponding. So you have three morphisms. You have three morphisms where these are the infinity categories underlying one simplices as before. And then you have, so yeah, let me call this F, F0, F1, F2, and then I have C0. So F0 has edges boundary C0, C1. Okay, let's do this like this, C0, C1, 2. Okay, anyway, it's the following diagram. So this C0, C1, they are the boundary points of F0. C1, C2 are the boundary points of F1, right? And so on. And this diagram commutes. So everything commutes. So everything commutes. And all of these maps have the same property of being full, faithful embeddings, which are cumulatively surjective on objects, and they're all quasi-equivalences. And you sort of keep going like this. So an n-simplex, keep going. Okay, so anyway, so the point is that, so I think I don't have time today, but tomorrow I will tell you how this vastly simplifies the story, because you can extract from this data an honest topological fibration that you can actually compute in various cases. So the point is that there is a certain universal fibration over S, which you can think of pulling back to X, and then you get a topological fibration. So starting from the data of a Hamiltonian fibration, you get a topological fibration. And so then instead of doing symplectic geometry, you're doing topology. So you get symplectic invariance from the topological invariance of that fibration, of that topological fibration. But you're doing honest topology. Anyway, so I think now I don't have time, so I'm going to stop here. Speaker. Right. I mean, so I mean, this is like, yeah, there's a lot of questions about S, right? So I mean, so like, right. So why this S? And yeah, question 2 is how to compute anything. And well, so what is S? Well, so it is. I mean, this S just naturally falls out of the construction. So this space, but it is basically some kind of it's nerve of some category where morphisms are like bimodules over infinity categories or something like that. So some kind of complicated. I mean, there is like some hypothetical infinity category of infinity categories where morphisms are bimodules. Well, I don't know what that is, but I can give you a concrete model for what I think it is. It is this simplicial set. And then, well, so the other reason why this S is good is because you can actually, because it's somehow very amenable to doing computations with this, because there is some fibration over this. Basically, so there's a fibration over this where the nerve over a point is where the fiber over a point is the nerve of the corresponding A infinity category. And then, well, so that fibration has very good properties. It's what's called a Cartesian fibration, which is kind of an analog of a Serre fibration. And so you pull it back, you get a Serre fibration over your space, and then you can do topology, just honest topology. Because and basically it's more than honest topology, because the point is that when you're doing topology, like something like computing homotopy groups of S3 or something, it's very complicated. I mean, if you want to think of it in terms of a simplicial set, it's extremely difficult. So you cannot use combinatorial techniques to do it. So, but on the other hand, for this vibration that you get, all the simplices are given combinatorially. So you can actually compute homotopy groups by hand, because all the simplices you know. they're given in terms of sort of morphisms in infinity category in various A-infinity relations. So it's kind of actually more concrete than working with a space like S3 or something.